In our last lesson, we started talking about entropy and Gibbs free energy. And in 17.5, the first part of this is going to talk about how you can also change the number of molecules in order to change the entropy. So we talked about how it's dependent on temperature. You can also change states of matter. But notice that in that reaction, you have a total of 9 molecules on the left, and they're getting that from these numbers. And then you have 10 on the right. And so because you have more particles, there are more possible positions, which means the entropy increases. And the third law of thermodynamics is included here, and this says that the entropy of a perfect crystal at 0 degrees Kelvin, which is absolute zero, where there's no movement, and remember we've never achieved that, but that would be 0, so there would be no disorder. And this is a hypothetical state that we haven't achieved, but this is what we measure entropy against. It's kind of like the standard. You're going to calculate entropy in some of the progress check problems, and this is the equation that you're going to use. Notice that it's exactly the same as a delta H equation that you used, except now we have entropy instead of delta H. So it looks super complex, but if you know what these symbols mean, it's not too bad. So this sigma right here means the sum of. So you're going to add together all of the products and then subtract the reactants. Do be careful and make sure you do final minus initial, so products minus reactants. And then these lowercase n's stand for the mole coefficients in the balanced reaction. So don't forget that you do have to multiply the entropy value that they give you by the coefficient in the balanced reaction. And those little zeros, it's called a knot, the little knot symbol that's on the delta S's means that it's in standard state. And standard state means like metals are going to be solids. It's whatever state it's going to normally be in at 25 degrees Celsius. And if it's a solution, then it's at 1 molar. And like I said, don't forget to multiply the entropy value by the mole coefficient. And then you just do products minus reactants. Notice that entropy is an extensive property, just as a review from that vocab word from our very first chapter. Extensive means that it does depend on how much you have. So the more particles you have, the more complex the molecule, the higher the entropy is going to be. And that leads us to 17.6, where we're going to calculate more of delta G. So first of all, keep in mind that delta G with the little knot symbol on it, again, means they're in standard states. And this is the change in free energy that will occur if the reactants in their standard states are converted to products in their standard states. This cannot be measured, it can be calculated. So we can measure other things, plug it into equations, and then we can calculate it. We care about this, the reason we're studying delta G and Gibbs free energy is because it allows us to compare what kind of reactions tend to occur. So again, we're looking at how spontaneous they are. So remember, the more negative the value for delta G, the more it's going to be spontaneous in the forward direction, which means the farther to the right the reaction will proceed as it reaches equilibrium. And again, equilibrium is the lowest possible free energy position. That's where delta G is equal to 0. So there are 3 different ways that you can calculate delta G, depending on the information they give you in the question. The first way is using the equation we did yesterday, which is this one. Again, it's in your reference packet, so if they give you information about the enthalpy and the entropy and the temperature, you can plug it in and calculate delta G. Again, be careful with this one and watch your units. Delta S and delta H almost always have different units when they give you that information. So usually one is in joules and one is in kilojoules, so just make sure units match first. The second method is very similar to Hess's law, where you have to rearrange the reactions, and this is extremely similar to Hess's law. So you're not going to do anything to the exponent like you did for equilibrium when we changed K. You're just going to do it to the value. So if you flip a reaction, you change the sign. If you multiply a reaction by a coefficient, you multiply the number for delta G by the same coefficient. And then when you're ready to put all your reactions together, you just add them up. So it's exact same as Hess's law, except you're just dealing with delta G instead of delta H. And then the last one is the same equation that I just talked about, except notice that it's now G instead of S. So you can also calculate delta G from the sum of the products minus the sum of the reactants. Just like with the S equation, you do need to make sure that you multiply each value by the coefficient in the reaction. This means the sum of, so you're going to add up all the products, add up all the reactants, and make sure you do products minus reactants. One thing to keep in mind is that delta G with a little f on it means this free energy of formation. So this is the change in free energy that accompanies the formation of 1 mole of that thing from its elements with all the reactants and products in their standard states. And these will be given to you in a chart. However, the amount of energy to form something that's already in its pure standard state is going to be 0. So for instance, if you had aluminum, just plain old aluminum metal, not bonded to anything or melted or anything, you don't have to do anything to form that. It's just in its normal state. And so the delta G of formation there would be 0. And they don't always tell you that. So if they give you a chart and you're missing some things, check if the thing is a pure substance in its standard state, and then the delta G would just be 0 for that.